Wi-Fi, Bluetooth, GPS, mobile phones, different technologies, but they all have one thing in common. They rely on radio waves. But have you ever wondered where radio waves actually come from? The answer may surprise you. They don't begin with something mysterious or exotic. They begin with something remarkably ordinary, a simple piece of metal. Here's something that surprises a lot of people. Antennas aren't made from rare metals or exotic materials from a high-tech laboratory. In fact, most antennas are made from ordinary metals, copper, aluminum, or steel. Nothing magical, nothing unusual. So that raises an interesting question. If an antenna is just a piece of metal, why can't a kitchen spoon transmit Wi-Fi? Why doesn't a paperclip receive television broadcasts? After all, they're made of metal too. The answer isn't the metal itself. The real secret lies in what happens inside the metal. More specifically, it's the motion of billions upon billions of tiny electrons. Normally, those electrons move randomly, with no overall pattern. But when they're forced to move together, in perfect rhythm, something extraordinary begins to happen. Their synchronized motion creates changing electric and magnetic fields. And those fields detach from the metal. Something remarkable happens. The metal starts producing radio waves. Inside every piece of metal, there are countless free electrons. Unlike the electrons tightly bound to atoms, these electrons can move freely throughout the metal. Even though the metal looks perfectly still, those electrons are already in constant random motion. But because they're moving in every direction at once, their effects cancel out. Nothing remarkable happens. Now imagine we connect the metal to a battery. The battery creates a voltage, an electric field inside the conductor. That field gently pushes the free electrons, and they begin drifting together in one direction. This is direct current, or DC. The electrons move with a steady, average flow, like water moving continuously through a pipe. But radio signals work very differently. Instead of flowing in just one direction, the voltage keeps reversing itself, over and over again. As the voltage changes direction, the electrons reverse direction too. They surge forward, then backward, again and again. Depending on the signal, this happens millions or even billions of times every second. The electrons don't travel from the transmitter all the way to your phone. Instead, they simply oscillate back and forth over tiny distances. Yet because billions of electrons are moving together in perfect synchrony, they create rapidly changing electric and magnetic fields around the conductor. And those changing fields are the first step towards something extraordinary. They allow the antenna to launch electromagnetic waves that carry information and eventually reach a receiver many kilometers away. This rapid, synchronized motion is the key that transforms an ordinary piece of metal into an antenna. Here's where things become truly remarkable. Whenever an electric charge accelerates, it doesn't simply move through space. It disturbs the electric field surrounding it. That disturbance can't remain in one place. A changing electric field naturally creates a changing magnetic field. And that changing magnetic field immediately creates another changing electric field. The process repeats again and again. Each field continuously generates the other, allowing the disturbance to travel outward on its own. Together, They become a self-propagating electromagnetic wave. This is one of the most beautiful ideas in physics. Once the wave is created, it no longer needs the antenna to push it forward. It carries its own energy through space, with the electric field and magnetic field continually sustaining each other as they travel. This also changes the way we should think about an antenna. The antenna isn't throwing radio waves into space like water spraying from a hose. Instead, it is rapidly shaking the electric field around it. That rhythmic disturbance spreads outward, creating new electric and magnetic fields, which continue reproducing themselves far beyond the antenna. The antenna starts the process. The electromagnetic wave does the rest, and that wave races across space at nearly 300 million meters every second, the speed of light. Imagine holding one end of a long rope. If your hand stays still, nothing happens. But the moment you move it up and down, a wave begins traveling along the rope. Notice something remarkable. Your hand never travels to the other end. Only the disturbance does. An antenna works in much the same way. The electrons inside the metal move back and forth, but only by tiny distances. The electrons don't travel across the countryside or into space. Instead, their motion creates an electromagnetic wave. And that wave can travel enormous distances, far beyond the antenna itself. Receiving works in almost the exact opposite way. As a radio wave reaches the antenna, its changing electric field gently pushes the electrons inside the metal. Those electrons begin moving back and forth in the same rhythm as the incoming wave. That motion creates a tiny electrical signal. And when we say tiny, we really mean tiny. By itself, it's far too weak to drive a speaker or display a video. But it doesn't have to. Inside your radio, your smartphone, or your Wi-Fi receiver, sensitive electronic circuits amplify that faint signal, filter out unwanted noise, and decode the information it carries. In just a fraction of a second, those tiny electrical vibrations become the music you hear, the videos you watch, the phone calls you make, and the web pages you browse every day. It's an extraordinary process. The very same piece of metal that launches electromagnetic waves into space can also detect waves arriving from thousands or even millions of kilometers away. No moving parts, no magic, just electrons, electric fields, and the elegant physics of electromagnetism. That's the remarkable beauty of an antenna. If antennas are just pieces of metal, does their size really matter? Absolutely. An antenna performs best when its size is matched to the wavelength of the signal it's designed to transmit or receive. Longer wavelengths generally require larger antennas. Shorter wavelengths can use much smaller ones. That's why an AM radio antenna can be several meters long, while the antenna inside your smartphone is small enough to fit on your fingertip. So, how do engineers decide the perfect antenna size? That's exactly what we'll explore in the next episode. Today we've discovered that an ordinary piece of metal can do something extraordinary. By guiding the motion of billions of electrons, an antenna creates electromagnetic waves, carrying information across the world and even across space. If antennas are just pieces of metal, why are some antennas only a few millimeters long, while others stretch for tens of meters? The answer lies in one fundamental property of every wave: its wavelength. I'll see you in the next episode.